Uh, Good afternoon. My name is Samir Llamazares, and I'll be talking to you about the work I did with Professor Tocino to study the stability of a model used to study the diffusion of malware in a wireless sensor network. So, first of all, I'll start by talking about the model we studied. So this isn't the model we studied, but this was our starting point. This is an established model which is used to study the diffusion of malware in wireless sensor networks. It's called the MDBCA. And I would have hoped that Professor Martín del Rey would have talked about it, but he's not present. So I'll give a brief summary. This is a compartmental SEIR model, so susceptible, exposed, infected, recovered. And it's a generalization of an agent-based cellular automaton model. So for this model, there is a known stability condition, which is that constant, the basic reproductive number, is smaller than 1. And this model is a deterministic model. So this means that this model cannot capture fluctuations, random fluctuations, which may occur in the spread of the malware. For this reason, Professor Tocino and I considered a slightly different model in which the incidence given by the parameter lambda was substituted by a constant plus some noise. This noise is used to capture the randomness present in the interaction between a infected in a susceptible node and also the chance of the infection spreading. So now we have, instead of a deterministic equation, we have a stochastic differential equation. This means that the solution is no longer a deterministic function, but rather it is a random function. In this figure on the left, we have the solution to the MDBCA, the deterministic one, and on the right, we have possible trajectories of the solution to the stochastic one. So as you can see on the right, there are several different trajectories, which is a result of the fact that this model is now random. So our analysis focused on one of the most important qualitative properties of dynamical systems, which is stability. There are several different kinds of stability, but the one we focused on is the one called asymptotical stability in probability. So let me briefly explain what that is. We say that the solution of the dynamical system, which I denoted by X, is asymptotically stable in probability if it verifies two things. The first thing is that if the starting point of the dynamical model, so x0, is close to the equilibrium point in the figure xc, then the solution, the dynamical system, x, will stay close. In the figure, it stays at most at distance epsilon. And the second part, the asymptotical part, is that in the time limit, when time goes to infinity, then the dynamical model will converge to the equilibrium points. So that's the stability that we'll be studying of the stochastic MDBCA model. So how do we do that? Well, for this model, we have only one equilibrium point, the disease-free equilibrium point, in which all the nodes are exclusively susceptible. And similarly to in the deterministic case, we can somewhat simplify this problem by studying, instead of the nonlinear equation, we study the linearized equation. So if this were just a deterministic equation, here in the linear equation, we would simply study the eigenvalues of this matrix M, and we'd be done. However, in this case, we also have a stochastic component. So we have to work a bit harder to study the stability. So to study the stability of the linear equation, which will in turn give us the stability of the nonlinear equation, we can use a theorem which relates the stability of this linear equation to the asymptotical stability of the second moment of the solution to this linear equation. This theorem says that if the the second moment of the solution to this linear equation is asymptotically stable, then the linear equation is asymptotically stable in probability. Okay, so in summary, we're studying this linear equation. If we see that the second moment is asymptotically stable, we will have achieved what we wanted. So the second moment, which we've denoted by P, is given by this differential equation. Note that this differential equation is deterministic, not stochastic, because once we take the average, the moment, this is now a deterministic equation. Okay, so we want to see if P is asymptotically stable in the deterministic sense. So to do that, first we simplify the problem a bit more. We note that the matrix that describes the second moment is symmetric. So we only need to study the lower half of the components. These components in green. If we call Z the vector formed by these components, then we have this differential equation. So now what we have to see is that the solution to this differential equation is stable. And this is now a very simple linear deterministic differential equation. So all we have to do is study the eigenvalues of this matrix M. The matrix M is a block diagonal matrix. So we study the eigenvalues of each of the blocks, and after manipulating several inequalities, we reach two conditions which give us that all the eigenvalues are negative, which in turn means that the solution is stable. These conditions are this first condition on one of the parameters, which is also a condition which arose in the deterministic system. And the second one is that a certain constant, which we call the stochastic reproductive number, is smaller than 1. Okay, so in conclusion, with this study, we reached the following theorem. If those two inequalities I mentioned previously hold, then the stochastic MDBC model is asymptotically stable in probability. And consequently, we have that this constant R0 is a sort of stochastic analogous of the deterministic reproductive number. Okay, let's finish off with some numerical experiments to illustrate the results. So in these 4 plots, we have the 4 compartments of the model: the susceptible, exposed, infected, and recovered nodes. The thick lines indicate the solution to the deterministic MDBCA model, and the thin trajectories are trajectories of the stochastic model. So in this case, both the deterministic and the stochastic R0s, the reproductive numbers, are smaller than 1. So in this case, the solution to both the deterministic and stochastic models are asymptotically stable. They both converge to the disease-free equilibrium. As you can see, the susceptible nodes converge to 1. That's the proportion of the susceptible nodes, and the rest converge to 0. In this example, where both reproductive numbers are greater than 1, we see that the deterministic model, given by the thick lines, converges to the endemic equilibrium point, whereas the stochastic one is unstable. As you can see, it fluctuates wildly. Okay. In this third example, we have the deterministic reproductive number is smaller than 1, and the stochastic one is greater than 1. So, despite the fact that the stochastic reproductive number is greater than 1, you can see that the solution to the stochastic model is also asymptotically stable. And this reflects the fact that our theorem was only a sufficient condition for stability and not a necessary one. So in some cases, the stochastic reproductive number may be greater than 1, but the stochastic system may be stable, like here. And finally, another example where both reproductive numbers are greater than 1, but in this case, the stochastic model does in fact converge to the disease-free equilibrium. So this is indicates that in some cases, adding noise to the model, we can stabilize it. In this case, adding noise made the stochastic model converge to the disease-free equilibrium. Okay, well that's everything. Thank you for your attention, and do you have any questions?
Any questions, anyone? No?